welcome everyone. Good afternoon or good morning. Thank you so much for joining us. We are really looking forward to the conversation that we'll have with you today. Let me quickly introduce myself and get some housekeeping items rolled out for our session here today. First of all, I'm Claire Gandy. I am the Sales Engineering Manager for the Building Products Group with Bekaert. I'm based in Atlanta, and if any of you have already started looking at some of the video tutorials for the software that we're going to be reviewing today, you may have already seen or heard me on those recordings. But I do really want to thank you. Hunter and I are excited to talk to you about this software. We are both structural engineers, and this is really a session geared towards the structural engineering community. So a few housekeeping items. So we will ask you to please use the Q&A feature of this Teams webinar to enter any questions that you have along the way. And we will get to as many of those questions at the end of the session as possible. If Hunter is unable to get to all of your questions, he will follow up with you after the fact. If you see a question come through that you also are interested in, you can use the like feature to indicate as much, and that will help us in queuing up those questions. This webinar is being recorded, so if you miss any part of it or if you'd want to share it with a colleague, you will have access to the recording later on. And if any of you are interested in receiving a PDH certificate for continuing education credit, you can email Hunter. I have put his contact information as well as my own in the welcome chat here, so you can go ahead and reach out to him and we can get you that PDH later on. So now that brings me to formally open the session and introduce our speaker. So Hunter Metters is a regional sales engineer with our team. He got his degree from the University of Cincinnati and then spent 5 years as a consulting structural engineer and attained his PE license. He joined the Bekaert team in April of 2023, and he covers the Cincinnati area as well as Indiana, Kentucky, the upper Midwest, and Kansas, and as far west out to Kansas City and Kansas. So in his role, Hunter focuses on providing optimized steel and synthetic fiber reinforced concrete designs, as well as educating the structural engineering design partners across the US that we work with. So hopefully some of you have been lucky enough to work with him up till now. And with that, Hunter, I pass it off to you.
All right, Claire, thank you. You can hear okay? Okay, good.
I can hear you. Yep, loud and clear.
Just doing the last check there. All right, great. So I trust everybody can see the presentation here. We're going to start a little bit with some background and some introduction to Bekaert, as well as sort of the brief overview of what the tool is based on as far as design, calculations, that kind of thing. We'll start there, and then we're going to dive into actually using the tool, running through some example problems, and showing the functionalities for you all. We won't do a super deep dive. We certainly can set things up with you individually in the future to have a more deep dive or specific project dive if you have anything you want to take a closer look at. But this is going to be very much geared towards some basic examples in how you use the online tool. So without further ado, the agenda that we're going to stick to for this first portion here, I'm going to go through some background about Bekaert for those of you who might not be aware of the size and scale and variety of products that Bekaert brings to the market. We'll talk briefly about that. We'll get into Dramix steel fiber concrete. We'll talk about how we go from a beam test, how we cast sample beams, test them, gather the data, and ultimately land at a bending moment capacity for the concrete sections. Talk about the design fundamentals of SFRC, steel fiber reinforced concrete. talk about some typical slab-on-grade applications, and then lastly, we'll spend the remainder of our time in the demo tool looking through, running some calculations, running some iterations, and spend the rest of our time in the tool itself so that you can get a decent grasp on kind of how the thing's going to function, what sort of results you can expect, and what sort of inputs you can expect to have to make. So that's our direction. We'll start with about Bekaert. So Bekaert is a global market and technology leader in the steel wire transformation and coating space. So we take raw steel wire and we draw it and shape it and form it into many, many, many different products in dramatically different parts of our everyday lives. Some of the biggest are in tire reinforcing, so the steel wire that is in tires for your cars. Bekaert does a lot of that to the tune of about a third of all the tires on the road globally have Bekaert wire in it, all the way to the construction world where we all operate in the steel and roadway reinforcing, plaster reinforcing, masonry reinforcing. I've got a slide on that here briefly. So all over the place, all steel wire transformations. To give you a little bit of the scope and size of Bekaert, so in 2023, we reported a consolidated sales of close to $5 billion with an EBITDA of 434 million in 2023. That's operating in 130 countries with 75 production plants scattered throughout and about 24,000 employees around the world. How that shakes out sort of on the map. Here in North America, we have 9 production plants. We also have some offices scattered throughout the United States and Central America. And we have one manufacturing plant in the US that specifically manufactures our Dramix steel fibers, which is relating back to the tool. That is the steel fiber choice that you're going to have when you're designing in the tool. We do have a manufacturing facility in Tannersville, Pennsylvania, sort of the Scranton area that manufactures our steel fibers there. Now, I mentioned that the building products, the construction building products portfolio of Bekaert is not just limited to reinforcing concrete. We also can do roadway reinforcing, masonry reinforcing, plaster reinforcing, and the like. But this tool that we have rolled out to the market specifically revolves around Dramix steel fibers for reinforcing concrete applications. So with that, let's talk a little bit about Dramix steel fiber concrete. So the principle of concrete reinforcement, we're taught this if you took concrete classes back in college. You're taught that concrete is very brittle and is not really worth anything when it comes to carrying tensile stresses and tensile loads. It is very low ductility. When it's subjected to those tensile stresses, unreinforced or plain concrete will ultimately crack and fail once the loading exceeds the cracking moment of the concrete. So how do we change this, right? Well, we add some level of reinforcement to the concrete matrix. This could be either a mesh, this could be a rebar, or in our case, steel fibers added. What our goal is there is to simply increase the load-bearing capacity as well as limit the crack opening of the concrete. That is our goal for adding reinforcement to an otherwise very brittle material. Now, steel fiber concrete specifically, steel fiber reinforced concrete is a concrete that has a homogeneous distribution of randomly oriented, discontinuous, discrete steel fibers. What that means is there's a bunch of individual fibers anywhere from 1.5 inches long to maybe 2.5 inches long, scattered throughout your concrete section, all over the place, oriented all different directions, and you achieve what we call 3-dimensional reinforcement. The entire length, width, and depth of your concrete matrix has reinforcement throughout. Now, when you're talking steel fibers, This is a direct swap, steel for steel, fibers for your maybe typical steel wire mesh or your rebar. But you're going from a continuous reinforcement in the case of rebar and mesh to discontinuous. The fibers are individual pieces, again, a couple inches long, scattered throughout your mix with an even distribution everywhere throughout the concrete. And that is the design principle and basis that we use in our designs, that the tool is using in its designs. So that is, in general, the big picture. What is steel fiber reinforced concrete? But when you go to design, what we're trying to find ultimately is what is the bending moment capacity of our concrete sections that we're trying to carry the loads, whatever we're trying to input into this tool, so that our projects, go off without a hitch. So how do we go from evaluating, concrete with fibers tossed in to ultimately providing values and bending stress values for you to be able to stand by your designs? Well, we cast a bunch of test beams with our steel fibers in there. And along with some ASTM tests that we do run, the industry standard in our world is the EN 14651 beam test for flexural strength of steel fiber reinforced concrete. The EN 14651 test is a simply supported beam. It is loaded at the midpoint. And if you notice on the picture there, there's a notch that is sawn into the bottom of the beam. What we're doing there is we're ensuring that ultimately we want it to crack there, but we are also going to take that notch and we're going to measure it as we load the beam, and that notch is actually going to open wider. It's going to displace. So we take readings of the corresponding stress that's being applied to the beam. We take the reading of that stress at benchmark openings of that notch. They're in millimeters. I'm trying to get them to switch to the good old US units. It's a tough sell, but in 0.5 millimeters, 1.5 millimeters, 2.5 millimeter, and 3.5 millimeter opening displacements, we measure what the stress is corresponding to that opening. Those give us what we call our FR values. FR values. There are 4 that we gather, one at each of those benchmarks. But here in the US, the 2 most important FR values that we capture is the FR1 value and the FR4 value. The FR1 value is going to give us our serviceability value. That stress is what we are going to use for serviceability checks. The FR4 value that we gather is what we're going to use for our strength designs, for when we're actually inputting the loads into the tool. So we take those values and we measure them amongst the different fibers that we have in our portfolio. We've had the 3D fiber. If you've been working with us for more than probably 2 or 3 years, you've heard us talk about the 3D fiber. Maybe years ago, you even had projects with our 3D fiber. It's been on the market in the US since roughly the 70s. We've been using the 3D steel fiber in the United States for decades. Along the way, we've innovated and we've bettered our product portfolio. We've bettered our steel fiber line. And now we have the 4D and the 5D steel fibers. And so what I'm showing on this graph here is a comparison in essentially your load displacement of each of those different fibers and illustrating what those strength differences are. The biggest thing between the 3 fibers that you'll notice first is the 3, 4, and 5 correspond to the number of bend segments at the end of each fiber. The 3 has 3 bend segments, the 4 has 4, the 5 has 5. Among many other things, that's kind of the biggest difference between them. But our 4D fiber has become our workhorse fiber, we like to call it. It is the lion's share of our projects in the last 24 months have been with our 4D fiber, as it is designed for optimal crack control and strength. It really combines kind of the best of all the worlds and captures most of the demand that we need to achieve can be captured with the 4D fiber. Our 5D fiber is designed for bending hardening behavior. So that is, if you're familiar, when the post-crack flexural capacity actually exceeds the modulus of rupture, the cracking moment of the concrete. When the post-crack exceeds that, that is bending hardening behavior in the concrete. And that is achieved with moderate dosages of our 5D steel fiber, and higher dosages of our 4D steel fiber also gets there. But our 5D fiber is really designed for those rigorous structural applications, and that's where we'll tend to see that fiber get used the most. So long story short, we cast these test beams, we run them through the beam test, we get all these FR values, right? And then ultimately we're able to determine the sectional moment capacity of our concrete using these test values. So we've gone from casting concrete beams to actual values, flexural capacity values that we can then provide for our designs in the online tool. This is a typical stress strain curve that I'm sure we're all used to seeing. Everywhere south of the neutral axis in a typical concrete member is not going to be able to carry any tensile capacity unless you have some kind of steel reinforcing rebar, something like that. When you have steel fiber reinforced concrete, you have tensile capacity everywhere south of the neutral axis, right? There again, it goes back to one of the first slides I introduced with. You have reinforcing in your entire length, width, and depth of your concrete section. Therefore, you have tensile capacity everywhere south of the neutral axis. And in the case of having some additional reinforcing, the principle of superposition applies. But in the case of a fiber-only design, you still count on having that tensile capacity everywhere south of the neutral axis. So let's briefly hit on the design fundamentals of steel fiber reinforced concrete. Let's take a slab, just a plain concrete slab. And remember, concrete's a very brittle material. So no reinforcing, plain concrete, let's load the slab. The slab's going to be able to carry the loading up to the point in which the slab finally cracks. And in a plain concrete section, once the slab does finally crack, you no longer have any moment capacity through the crack of that slab, right? The post-crack flexural capacity is 0. The first crack is the last crack in a plain concrete design. Now, how does that differ from our steel fiber reinforced concrete design? So we actually look at this in a plastic analysis lens. Same slab, and we start to load it, okay? We like to say the fibers are asleep until that first crack occurs. They're really not doing much until the slab finally cracks. So we load it. Finally, we get that first crack that starts to form, and then we say the fibers wake up and go to work. Now that that crack is there, the fibers will then start to redistribute those moments that are being generated in the slab due to the loading. It will redistribute those moments to the top of the slab. And what you'll find is the formation of these yield lines or cracks, also plastic hinges that is going to redistribute those moments in the bottom and top of the slab section. That then allows us to be able to utilize much more of the capacity of the concrete rather than a typical elastic analysis would allow. So if we briefly take a look at both of those options, an elastic versus that plastic or yield line theory analysis for your slab. Well, we're going to determine demand moments in 2 ways, right? From your elastic calculation, you might run a finite element model, gives you your demand moments due to the loading. But what it's not going to do with your concrete slabs, it's not going to consider the redistribution of those bending moments. Therefore, it's going to lead to an inherently conservative design approach when you're talking about a steel fiber reinforced concrete section. On the flip side, when you are using a plastic calculation or the yield line theory that our tool is based on, the yield line theory, it is going to consider the redistribution of those moments from the bottom and top of the slab. And it allows the steel fiber reinforced concrete to utilize that bending softening behavior. And it allows for more capacity to be utilized in these loading scenarios rather than your elastic design. It's an iterative design process. There's a large number of parameters that must be inputted, not limited to just thickness and compressive strength and fiber type and dosage, right? There are soil characteristics, the friction between the slab and the soil, the subgrade modulus, the geometry, the loads and load locations, whether the loads are dynamic or static, right? There's all these different factors that you're going to be able to input into the tool that's going to spit out the best design, taking all these things into account from a plastic analysis perspective. So for slabs on grade, the most common standard industrial floor, the most common way that we are going to induce joints and contraction joints and relieve the slab is saw cuts. And I would venture a guess that probably 3 out of 4 of the slabs that you all are going to use our tool to design are going to more than likely be saw cut slabs. It's the most common industrial slab construction method here in the US. It's very efficient in producing contraction joints, but there are some things to keep in mind when you are still specifying, even though it's a relatively standard solution, there are still some things to keep in mind when you're specifying a saw cut slab with steel fiber reinforcing. The biggest thing is the saw cut depth itself. So we're probably all used to a D/4 for your saw cut depths. The ideal joint depth for a steel fiber reinforced slab, we want to see a third of the total slab thickness. So we cut a little bit deeper than your typical D/4 recommendations, but we don't want to cut so deep that we can't still get some of that aggregate interlocking beneath the saw cut, because then we could have some load transfer concerns at that point. However, on the flip side, when the saw cut is too shallow, there certainly is a case that you could see some random cracking out in the panel because you're not allowing the slab to relieve itself at your saw cut joint, right? Remember, the point of saw cuts is we're telling the slab where we want it to crack. That's the point of the saw cut, right? So when it's not done correctly, we can have problems like in-panel cracking, random cracking, and things like that. So as you design these in the tool, again, while they are kind of, you might feel like they're really straightforward and you design them all day long, there are just some things to keep in mind, and we want you to be aware of as you go out and start to design slabs using our tool. Now, the advantages of saw cuts are great, right? Consistent joint dimensions, same width and depth at each cut. You know, when a contractor is really on their game, the cuts are nice and straight and clean, good looking. You know, panels are all the same size, good looking, cost effective concrete placements, right? And we're not really limited to the size of the concrete placement because we're going to relieve the slab every, let's say, 15 feet each direction or 20 feet each direction. So as much as we can place and finish, we're going to be okay. And we're going to minimize random cracking with the saw cuts. So it is a really great solution still out in the market. Some possible problems with those traditionally jointed saw cut floors, problems that ultimately lead to a negative impact on your floor, could be any of the combination of the items I show here. Cracks, curling, rocking slabs, spalling joints, poor load transfer. Any one or a number of these things could occur in a traditionally jointed floor. And any one or a number of those things could lead to then high repair budgets for the floor, high repair budgets for any equipment that you're running on the slab, could lead to reduced operational productivity, reduced property value, increased healthcare costs for operators should anything bad happen while they're going over the joints in their equipment. right? So these are all things to keep in mind as you're out there designing your typical saw cut slabs in our tool. These are just some things to keep in mind that we may need to bring those up to the owners, to the design teams, say, hey, have we thought about X, Y, and Z potential issues that could happen in the future? Now, our tool does have functionality to mitigate a lot of those concerns. The second most common floor type, I would say, in the United States, a jointless slab. If we've come to talk to you in any capacity on steel fiber reinforcing and our position in the market, I'm sure we've brought up the solution of a jointless floor. A jointless floor is no saw cuts, right? We could go upwards of 130 plus feet in each direction with construction joints, no saw cuts necessary. When you construct these jointless floors, the panels can be anywhere from 105 feet, let's say, to 140 feet, right? Maybe even more in certain cases. And they're shaped, these construction joints are shaped using these factory produced joint profiles with dowels installed and integrated protection for the edges of the joint. These are full depth doweled profiles that we recommend you include on your jointless slabs. Now, why am I even talking about the jointless slabs, right? Our tool has functionality to design these. I'll talk in just a minute about the basic user and the advanced user of our Dramix Pro tool, but you can get into designing the jointless slabs in our tool. Now, what I want to stress, designing a jointless slab goes far beyond just getting a dosage and a thickness and joint spacing. It goes far beyond that. So while the tool, if you're an advanced user, and you'll see in a few slides, while the tool will allow you to do this, please, we highly recommend, if you want to go down this road, we highly encourage you to reach out to us and allow us to put another set of eyes on things with you, help you look over details, help you plan so that you're giving your project the best chance of success. I'm going to talk briefly then about the 4 key fundamentals for a jointless slab, but again, this is not going to do it justice. The care that is necessary on these projects is far beyond what we're going to talk about in our time here today. The design, the planning, eliminating restraint, and execution of the slab are really the 4 key fundamentals for a jointless slab to be successful. So the design portion, we get joint spacings, we get a dosage, we get a thickness, and we feel like we're good to go, right? However, there are many other considerations, such as, double layer of slip sheet below the slab to ensure that our slab can float and shrink up, and those shrinkage stresses aren't going to get too high if the slab is restrained. Anything that is going to cause restraint in the slab, such as columns, bollards, drains, truck docks, we want to make sure our jointless slab is isolated from those things, right? It really is all in the details when it comes to these jointless slabs. So again, I want to stress to you that you can become an advanced user of our tool, and that allows you the functionality to design these more complex slabs. Highly encourage you get with your Bekaert rep just so that we can help coach you through some of these nuances, because there are many. It goes far beyond, again, just spitting out the output from our online tool. So to briefly look at just the two flooring types that we discussed here, the saw cut slab, right, most common. Again, maybe 3 out of 4 of the slabs that will ever get designed in our online tool are going to be saw cut here in the US and North America. But for those more sophisticated solutions where you want to look at the jointless floor, right, there is some major advantages to a jointless floor, but there's also some very extra care, a very high level of care we must take as we go through designing those. So now I've mentioned a couple times the basic versus an advanced version of our online tool. Both are free to use. Maybe I should start there. Both are free to use. The basic version is going to have limited functionalities. You will still be able to go in and design a saw cut floor for just about any type of project you may have. If it's a saw cut slab, you can run a fiber only solution and check to see if you can get there, obviously inputting your loads, your soil conditions, things like that. That's going to be all day long in the basic version of our online tool. There is an advanced version that then opens you up to those more complex slab solutions, right? Again, that is going to be, we are going to hold that door. We're going to hold that door pretty tight on who we approve essentially to be users of the advanced version. And we have many reasons for that. But we want to make sure that we're not doing anything that's going to set our partners up to get into a bind because we didn't coach properly enough before we approved somebody to be an advanced user of our tool. What you can expect if you do want to become an advanced user, you can definitely expect that it's not an instantaneous approval. So if you're running the basic version and you apply to be an advanced user, it's not going to be instantaneous. So I definitely encourage you to not wait until the project is due, a project deadline or whatever, to try to become an advanced user. There is a process. It very likely could involve a brief meeting, a phone call, certainly some email exchanges between us and you, just to make sure that we're covering all of our bases and we're setting you all up as best we can to use the tool successfully. So if that is of interest to you as you go through the tool as a basic user and you're like, I really, I do want some jointless capabilities. I want some of those more complex slab options. We can certainly, file to be an advanced user, and we'll get with you on making that happen. All right. So with that, I think we've set the stage. We're going to talk about now getting into the tool with a sample project. So this is going to be a very typical type of project that would be common for us to see. I'm not using anybody's project that was sent to me. Don't worry. This is not I've not taken anything that one of you all have sent. This is something we created for the demonstration purposes. So very commonly, we're used to getting some kind of pallet racking in these facilities. Typical industrial slabs include some level of pallet racking loads. So in this case, we're going to run point loads of 18 kips. We're going to have the racking back to back set up at 42 inches with a 12-inch gap and then 42 inches. We're going to assume in this case that there is no free edge concern. And briefly, real quick, the free edge of your slab is just the very outer extents of the slab, right? Pretty close in this picture. We would consider this edge, if I'm going off of this drawing here, pretty much a free edge there. For our case in the design tool, we're going to assume that you can't have a fully loaded rack leg there. So we're going to say there's no free edge concern in this case when it comes to racking. All right. We're also going to have a uniform distributed load of 750 PSF. And we're also going to input a forklift wheel load of 6 kips per wheel with a wheelbase of 36 inches and a wheel pressure of 200 PSI. Now we're going to start with a 10-inch saw cut slab, 4,000 PSI concrete. We're going to assume a soil subgrade modulus K equal to 130 PCI. And we're going to run the design using Dramix 406560 BG steel fibers. The Dramix 406560 BG is the most common fiber that we use in the market in the US here today. All right. So with that, I'm going to close out of the PowerPoint, and now I hope you're seeing the tool. Let me back up to this screen here. Actually, this is the screen that you originally came to for Discover the Tool and register for this webinar. Oh, by the way, I have another screen. That's why I'm looking over here. So if it looks a little goofy, if I'm kind of looking off to the side, that's why. So we have a tab to discover the tool. We have a tab for registering for the webinar. If we go to discover the tool, it's going to ask you if you don't have an account yet to register. The registration is simple. Again, this tool is free. It is not a software that you download to your computer. It is an online cloud-based tool. All right. So once you register your account, you get your email and your password, and then it's a sign in. And we're brought to your dashboard of where all your projects and your project folders will be placed. So this is our main screen. And as we get into the projects, you'll see this left-hand ribbon changes some, but these are my folders I have set up and different projects in there. So if I wanted to go to create a project, I would click here. Or if I wanted to add a new folder, if, this is, let me go back real quick. If I wanted to add a new folder that I wanted to call webinar, save. Now I have a new folder down here for webinar down here. And I can click create a project. And this is your first page that you will have to provide inputs for when you drop in to start a new project. So enter a project name. I have a bunch of test ones in there. My most recent one, I am located in Cincinnati, as Claire said. So Project Bengals was the title of my project. So Project Bengals, the folder, I've got a few. I'm going to click webinar to put that in my webinar folder. The object, you can put whatever you want here. A lot of times we'll put slab on grade. You may want to put the thickness that you're targeting. We could put in 10-inch slab on grade, something. We put in the location of the project. I typed in 123 Street, right? Whatever your address is of your project. Your remarks box can be whatever you want to show up. It'll show up on the calculation report. If there's anything in particular you feel necessary to put on there, if it's a certain iteration of the design that you're shooting for, or what have you, that's where you can drop that in. The date should automatically populate to today, whatever day you're inputting this. You can also upload a cover. So this could be like a cover photo for your project. Then you enter in your customer data. So who are you creating this design for? I typed in Cincinnati Bengals, 123 Street, Cincinnati, Ohio, whatever the address is, and then the email of your contact. So I'll just type in, since I don't have Joe Burrow's email address, I'll type in huntermetters@bekaert.com. Phone number, right? Website, whatever you want to include for your customer. Remember, this is your customer who you're providing the design for. Now your project settings, your last column here over to the right that we have to input before we can start to get into the tool. Your signature line is for your calculation report. We typically default to just not shown on printout. Your entry field units, well, this is the United States for probably most of us in here. So I'm going to click United States customary. And then for concrete code, I have different options here. So again, this tool, just a brief aside, this tool is for 130 countries around the world, right? While we operate in the ACI 318, you're going to see things probably in the tool that you're like, that's weird, but it's probably being used in some other country, right? So we've entered in everything. We've got our project data. We have our customer data. We have our project settings. Now we can go ahead and click save. You can't move on to the next step until you save this. So we click save. Now this blue button for next is illuminated, and we can actually get to the next step and get into the tools. For today, we just have a tool, slab-on-ground, open for use on this website. In the future, our goal is to hopefully introduce some more of our tools that we are already using internally. But for today, the slab on ground is the only one that we've released for the market. So it's the only option you're going to have, slab on ground, blue button next again. All right, now we're finally into the tool where we're going to start inputting some of this information. You'll see across this top part here, you have 4 words: setting, structure, material, loads. Each of those are essentially a tab that's going to require input in each of those tabs. So we're starting, good place to start is in the settings, right? In our design approach, if you go to this drop down, what you're going to see is, again, country specific inputs. We're in the US, so we're going to click US BD19 and ACI 318. The US BD19 refers back to our IAPMO report, which, if again, I go back to if we've come and talked to you at any length, you've heard us talk about our IAPMO report, which is our code document, which also houses all of our design equations that we use and that this tool is going to use when you use the US BD19 ACI 318 version. And that will be included in your calculation printout. Those calculations, those equations, where they came from in our ATMO report, all that information is going to be included in the calculation reports that you generate. So we're going to click USBD 19 ACI 318. The next one down, we're system capacity. We click that. Again, for the basic user, we're going to just leave it as design approach. There are some different things that could mean different things in different countries, right? For us and for the basic versions, we're going to leave design approach. There's also these, I should mention, there's these drop down, these eyes that you can click that will have some information on what each of those selections means. So I click the one for approach up there for the USBD 19 ACI 318, country USA. Bekaert SOG if you're operating in Belgium, right? DBV if you're in Germany, etc. So you can get some information on what those inputs are by clicking that little eye with a circle around it. Info button. Our country dependent settings, next setting here, USA, right? Concrete age at loading. We always default to just 28, right? We're going to assume that it's going to be 28 days of set before we're going to load the slab. Our next section is where we're going to input our safety factors and our load factors for the project. And I should note, just because we're filling this out now doesn't mean we can't come back and edit it once we get into messing with the tool. You can click between these tabs at any time when you're running your design. So don't feel like there's not a workflow that you must follow. But it's here, safety factors. We have our strength reduction factors. So all of our designs default to a strength reduction factor, as you are used to any kind of your fee factors that you use in your designs for 0.9s and for your bending and your shear fee reduction factors. We do the same thing with our steel fiber designs, right? And then we also have load factors in which we amplify the loading that gets provided with some kind of, typically 1.2, but could be whatever you determine. You are the structural engineer of record for your project. So you can adjust these load factors anywhere from 1 to 2, however you see fit. We typically default to a 1.2 load factor for our loads, unless we're directed otherwise by the structural engineering team. So we've entered in what we want to enter in here. It's a really good practice to get into, to click save very frequently when you're operating in our tool, because it's so easy to jump between tabs and jump between entering information, and you forget to save, and for whatever reason it doesn't save, and now you've lost a little bit of that input that you've done. It's very easy to forget. So try as best you can to get into a habit of clicking save and locking in your inputs as you go through. So that's our settings tab. We'll click over here to the structures tab. It doesn't default to jointless. it is on jointless, but it doesn't default to that. For the basic, you will have just a saw cut floor option there and under this slab type. As an advanced user, you will be opened up to some of these other options, including a jointless floor. But we're going to start saw cut floor, 10-inch saw cut floor. We're going to start there. Your slab exposure, indoor or outdoors? Is it an inside slab or is it like an exterior outdoor application? What are your ambient conditions for the slab? I know many of us, I know in our world, we deal a lot with cold storage. So if you're designing some cold storage, that's a very good case to think about inputting a very cold condition on your slab. Most of the time, typical slabs where you're going to have personnel and folks walking through there and fork trucks and all the kind of mess, very, very typical slabs, we just leave it as a tempered slab for ambient conditions. All right, now we're into slab thickness. These boxes you can click in and enter hard code any of the values. You can also use the slider, but the sliders, personally, I think it's just easier to enter in because, you can kind of see I can really only get between 9.95 and 1010. So I usually just double click in there, click 10, and we're off to the races there. So on a 10-inch slab, again, we're saw cutting. For panel size, let's assume 20 feet. 20 feet's a good number for our panels. So we'll drop 20 feet in here. And then we have a maximum panel ratio that we can input. If I knew that in every case my saw cuts were going to get cut in 20 by 20 everywhere clean as can be, sure, I would be inclined to leave this at 1. But just on the off chance that, hey, one of them gets cut in 21 by 18, 20 by 18 and a half, something to that effect. I personally, when I work with you all, I typically drop in a 1.25 for my panel ratio. That way I have a little bit of give in the event that there's a panel that's not exactly square 20 by 20. Just practice that I've done. Again, you're the engineer of record on this project, so ultimately your choice. Your primary joint. For a typical saw cut slab, our primary joint, we default to a doweled joint. Could be a smooth dowel, could be a plate dowel, could even be a diamond dowel, but it's going to assume just a typical doweled joint. And our default load transfer efficiency factor right here is going to default for this case to 0.7 for a load transfer efficiency. 0.7 for a doweled joint. All right. Our secondary joint is a saw cut slab. The only option is going to be a saw cut. That's our secondary joint. It'll be important to note that once you get into the load portion and then your calculations, when you are seeing references to primary joints and secondary joints, the primary joint is talking about your dowel joint. The secondary joint is talking about your saw cuts. All right. For your auxiliary reinforcement, this would be if you had, and this is not for the basic version, this would be an advanced version question. Do you have some other reinforcement you're including? And in that case, you can drop that in, whether it's top and bottom, double mat of something. For the basic user versions, you're only going to have a fiber only option there. All right, so we'll leave that at fiber only. And now we're down to our sub base and subgrade. So if you go back to my slides, right? Maybe you saw all those slides all over the place. What the heck is all this about? I'm trying to illustrate all of the different components that get inputted into this tool and spit out a very detailed calculation report. There are many, many factors that go into this, again, far beyond just a thickness and a dosage of steel fibers. So now we're down to subgrade, subbase. We're going to click in here for the soil model. And I have some different values here I can go through. For your basic user version, you're only going to be limited to your K value. And for most of the projects we deal with, that's sufficient, right? If I think back to my slides, I said 130 PCI for my soil modulus. So that's where I enter that there. If there was an insulation layer or something like that, I have the ability to include that. Most of the time, I'm going to leave that at none. After I finish entering any values into any of these tabs, if you scroll down and you see the blue back button, I personally think it's good practice to use that button rather than clicking back off the ribbon here or clicking this arrow, just in the event that something doesn't save. I've found that when you do click the back button, you really mitigate any kind of those concerns. So just a little best practice that I personally have noticed. Now we have our separation layer we have to call out. I have a few options here. I have one layer polyethylene foil, which just means slip sheet, right? None or to be specified. I typically leave it to be specified personally. If you know, again, as the engineer of record, if you know differently, you can put none, you can put the one layer. We usually default to be specified. As I mentioned, now that I'm done entering in all this information here, really good time to click save. Locks everything in. Now we can move on to our materials tab. And I'm sure you've noticed our nice graphical representation of our slab has changed as I've changed the inputs. Now we've got the dowels in there, we've got the saw cut in there, right? So now we're over to the materials tab. Concrete class. It's going to look weird because it defaults to C25-30. Click in there, it's all PSI, right? So we said 4,000. I'm going to drop 4,000 in. Now we're into fiber type. We called out a 40 65 60 BG steel fiber. That's this one right here. All right. This is the most common fiber being used in our projects in the United States today. We have other fibers in here. This is the one that is certainly the workhorse fiber of our portfolio as of today. So I'm going to use that fiber. You can see it changes here. It changes this to 4D. And now we have the purple fibers in the slab. You can actually see if you look close, it's a profile of the 4D fiber. You can see the extra hook on the end of the fiber. Now we're at calculation type based on dosage, residual strength, and performance class. Leave it dosage. Those other clicks are, we can input the FR values, but you have to have the FR values to input those. And I'm not sure even the basic user version is going to be able to access these. I think you're probably just going to be limited to dosage, but if you're not, I would just always default to leave it on dosage and go from there. All right. So 4,000 PSI, 4D, 6560 BG, dosage, and then here's where we input. Again, it's got another slider. You can slide your dosage. I don't like doing that, so I click in here, and we're going to start with 19 pounds per cubic yard. Now, why 19? If I've met with you or helped you design projects in the past, I've probably mentioned that for 40, 65, 60, 19 pounds per cubic yard is our minimum dosage that we will recommend on a slab. It will allow you to go less than that in the tool, but it's our best practice and it's our minimum recommendation that we're going to provide is 19 pounds per cubic yard. So I think I clicked save, but I'm going to click save again just to, it's a good habit to get into, just to save all the time. All right, we're in the last tab now. Loads. This is where we input all of whatever we're given by our racking vendors, our owners that are going to be operating their forklifts, whatever they provide us, this is where it goes in. Let's start with the point loads. So if I go back to my slideshow briefly, let me swing it over to this sheet here. I said we're going to run 18 kips, 42 by 12 by 42 with no free edge concern, 750 PSF UDL, 6 kip per wheel for my forklift, per wheel, remember per wheel, and a wheel pressure of 200 PSI. Let's go back to the tool and start to drop that in. For my point loads, you can actually get pretty differentiated and pretty unique inputs here. We can do a single point. We can do 2 points in a line, 3 points in a line, 4 in a line, 4 in a rectangle, right? We have all these different ways we can drop these racking loads in. It's our experience that more than likely 4 points in a line are going to be the controlling load case. So I'm going to drop that in and run with that. So 4 points in a line, and where these blue boxes represent where we want to apply those loads on our slab. So this first one here, you see this darker rectangle here in the middle of our lighter rectangle. This is our load location, and this indicates it being in the center of your slab panel. So we're certainly going to check that. We want to check the racks at the center of the panel. This one here just to the right, it's up against this solid blue line. Well, if I go over here and figure out what the heck that is, I have a joint type 1 or primary joint. So remember, primary joint is what? It's our doweled joint. Our joint type 2 is our secondary joint, or in this case, it's our saw cut. So this button here is asking me, do I want to analyze this rack load perpendicular to a saw cut joint? We found that it's the best practice to include that, because then we can allow for our racks to be however close or far from the saw cuts as we want, perpendicular, or the other option is directly below, parallel. I'm going to click both of those. That way we can represent the racking anywhere as it relates to a saw cut. The next two are your primary joint locations. Again, I want to design my facility to allow for those loads to occur anywhere near a primary joint, perpendicular or parallel. So I'm going to select both of those every time. This option down here and this option down here are up against this dotted line. That is your free edge of your slab. If I knew I was going to have a fully loaded rack at the free edge, and when I'm talking the free edge, I mentioned, I'm talking about the outer extents of the slab. When I'm talking the free edge, the outer extents, if I know I'm going to have a fully loaded rack leg there, I'd be inclined to click and check it there. For this case, we said no free edge concern, can't get a fully loaded rack leg there, so we're going to leave that blank. Also, your corner of your saw cuts, we typically leave that blank as well. If you find reason to click it, by all means, you can select it as well. We typically leave that one blank. This is our standard practice for when we're inputting rack loads into our tools. So we have our loads, we have our locations. Now we're going to input the actual magnitudes and some of that follow-up information. So I said 18 kips. So this is in pounds, the 18,000 pounds. Again, the sliders are there, but again, 18,000. Now it says load F1 and load F2, right? What the heck does that mean? Well, if you look right over here to the right, you have a graphical representation of the 4 points in a line. Load F1, load F1, load F2, load F2. Someday, are we going to be able to input a separate load for each one of those? Possibly. But it's our experience that most cases, it's a fair assessment that two different loads, F1, F1, F2, F2, work just fine for these applications. This also tells you your distance A, B, and C. Well, if we go back to the slides, we said it was a 42 by 12 by 42. So our distance A, we're going to set to 42. Our distance B is in between those two, the closest space rack legs. We're going to say that's 12. And then our distance C is that last space. We said 42. I didn't mention what a base plate size would be. I'm going to default to a 6 by 6. You all are typically great at telling me what that needs to be, but I didn't list one out, so I'm just going to say 6 by 6. Now, you can see that all of these values correspond to this graph. So you're able to go in and see like, okay, what do I mean by X and Y, right? X, Y, well, it's right here listed out. What about X prime, Y prime? What the heck, right? As we go down and drop in the load position, that's where your Y prime and your X prime come into play. So we can set these racks a certain distance off of the joints. We can set them 6 inches, 12 inches, 24 inches, right? Or we can leave this set to 0 so that the program assumes the loads occur directly on top of the joints, directly on top of the saw cuts. You have the saw cut and the dowel joint here. We typically leave those set to 0. That way our racks can occur anywhere on the slab. We aren't limiting ourselves to where they can and can't occur. So we typically leave those set to 0. So with all that entered in here, 18,000 pounds, 42 by 12 by 42 on a 6 by 6, I think we're good with point loads. I'm going to click back. And again, good practice, click save. So I'm going to save. Now I'm going to move on to my wheel loads. You can enter in a whole bunch of different wheel loads. We had a 1-axle, 2-wheel condition for a forklift. 1 axle, 2 wheels, all the same load positions, except now you have to think about, could my forklift ever drive out over the free edge of the slab? Like, I don't know, out into a parking lot or a truck dock area? Most of the time that answer is yes. So we actually click every single one of these for your forklift wheel loads. We like to typically see every single one of those checked. Again, you just have to conceptualize, where can that load occur on my slab? So I'm going to check all of them. My wheel load was 6 kips, 6,000 pounds. Again, this is entered per wheel. This is not your axle load, so keep that in mind. This is 6,000 pounds per wheel. So it'd be like a 12 kip axle. My distance apart was 36 inches and my wheel pressure was 200 PSI. All right, good enough. Now I can call out where my load is going to occur as it relates to the joints and the free edge. Well, I'm going to set all these, just leave them at 0, because I want to be able to say this forklift is designed to go over any element of my slab, the free edge, the saw cuts, and the dowels. I'm going to click back. Now I'm down to my uniform distributed load. You have 3 options. You have your worst case, which is the most conservative approach, which we're engineers, we love that. Worst case, you can look at several defined blocks where you can actually input the blocks in the aisle between them, or you can do one single defined block. We usually always go with the worst case. I said it was 750 pounds per square foot. That's what we default to. Again, you're the engineer of record. This worst case is going to analyze 2 at the magnitude of 750 PSF, 2 separate cases at a certain width, and then an aisle between them. And what's happening there is it is trying to maximize the moment stresses, specifically the negative moment that's going to occur in this aisle due to these uniform distributed loads. So it'll actually show you in the calculation report. It runs through a bunch of iterations to see what truly is the worst case. And it'll actually tell you it's a 200-inch wide with a 18-inch gap between them is the worst case for this slab based on this loading. So you'll actually see that in the calcs. Click back. So we've entered in those 3. I wasn't given any line loads, but your project may have line loads, right? There could be a partition wall that's got some loading that needs to be included, or maybe a CMU wall that's sitting on your slab that you need to account for. That's where you would enter in this for those applications there. You're entered in a single line or a double line load. Is it applied at the surface or at a certain depth? Typically, we leave at the surface. Then you can set your line load F magnitude, your width. Again, kind of picture a CMU wall, a block wall with a width of 8 inches, whatever it might be. And then you can apply it again to what locations. Slab center, always, is it going to hit a primary joint? Is it going to hit a secondary joint? Is it going to hit a free edge, right? Same, now you can kind of see the repetition here a little bit. I'm going to turn this off because I didn't set out any of these as a part of our design project. So to turn any of these cases off, you just click the square box at the very top of each of the categories. I click that, and now it's all gone. I'm going to click back. I've entered in my loads. I'm going to click save. Now I'm at the point where if I go to materials, I've got my dosage. If I go back to structure, I've got 10-inch, 20-foot each direction saw cuts. I got everything entered in, 130 PCI, got my loads inputted. I like to go back in and check just to make sure the loads didn't not save or something. If I go back in, 18 kips, 42, 12, 42, everything looks good. So therefore, we're at the point in which let's calculate final result. This is running, give a little bit of credit here. This is a dense software. There's a lot that it's calculating, so it does take a couple minutes to produce the value and the results. And now we're there. Now we're in the results view. We can see our point loads are utilizing the slab at 73%. Our wheel loads are only utilizing 29%. Our UDL is utilizing 57%. We didn't have any line loads, so it's 0 as it should be. You can go down and look at each of those represented by their load location. So what's controlling the 4 points in a line design, right? It's the parallel to your secondary joint. So that's your saw cut, right? So that makes sense. The weakest point of the slab, controlling the design, 73% utilized. We can click over to wheel loads. What's controlling our design there? What was the value? 29%. Parallel to your free edge, controlling the design for the wheel loads. And we can also do that for the UDL, right? The slab bending is controlling there. So we have all that information, and now we have a design. That would be great. However, 73% sounds like we got some room to optimize the slab a little bit, right? So let's go back and see if we can't get a little bit more drilled in, sharpened the pencil with our design. So I'm going to go back to the loads piece. I'm not going to change anything. I'm going to leave these in. I'm going to go back to the materials. This is where I could do some editing. I could change the dosage, right? Which I will here in just a second. But what I'm going to start with is going to the thickness of the slab. And I'm going to actually drop it, let's say 8 inches. Let's just see where 8 inches lands, right? So I switch that to 8. And what I can do, instead of having to go all the way to the end again, I'm going to click save because it's a good practice to do so. But I can view interim result. Again, it takes a minute to load. Sorry for the pause, but so I have a red failure you can see on the right, 109% red failure, no result, check input. If you get something that's over 100%, it is going to say no result, all right? So we have to do some adjustments. We either have to change the thickness or change the dosage. I am going to modify our dosage. Just going to take a stab. Let's see what 33 pounds per cubic yard gets us with an 8-inch slab. Again, we haven't changed any of the loads or anything. I'm going to click save. I'm going to run view interim result. %, and we work. So I took a 10-inch slab with a minimum steel fiber, minimum Dramix 4D steel fiber dosage, took 2 inches off the slab down to 8, 33 pounds per cubic yard of fiber, so a little bit more fiber, but 33 is certainly a manageable dosage of fibers, and we're at 95%. Our standard operating procedure is we cap at 95% for our designs. We don't want to run you out a design that's at 98, 99%, because we understand what Claire mentioned. We're structural engineers before we came to Bekaert. We understand there's some gaps, there's design changes in the future and things like that. So for us, we cap at 95%. So for this project, I just optimized 2 inches off my slab, added a little bit more fiber, not a lot more fiber, but a little bit more fiber, and I can get there with that design, an 8-inch slab with 33 pounds per cubic yard. So that is what I call and what we call the optimized slab design there. All right. Now, the last thing we're going to take a look at, what if we have an owner that's like, hey, run me up an option for a jointless slab. Let's just see what it looks like. What could you get? Where could we go? All right. Well, we're going to adjust the dosage. I'm going to bump it up to 40. The reason I'm going to do that is because that is our minimum dosage for a Dramix 4D 6560 jointless slab, 40 pounds per cubic yard. So I'm going to drop that in, click save. I haven't edited anything else. I've just moved that dosage to 40. Loads stay the same. Now we're into the structure. So if you have the advanced version, this is where you can get in here, select jointless. And now a few things have changed. So we have to go through and check our inputs. Our slab thickness. Let's just start with 7. See where 7 goes. Our maximum panel length. How wide do we want to check these panels? I'm going to put in 130. Okay, we'll just start there. Panel ratio, same spiel I gave earlier, same thing. I like to do 1.25 for this. 1.25. You see this switch to a dowel profile. That is going to happen automatically for a jointless slab. We are going to assume that a doweled profile is being used, which also changes the load transfer efficiency factor up to 0.8 from 0.7. The reinforcement is fiber only still. Soil model doesn't change, 130 PCI. Our separation layer on our jointless slabs, our best practice is 2 slip sheets below the slab. I'm going to select 2. All right. Everything looks good there. Jointless slab, 7 inches. Go to materials. Concrete class, 4,000 PSI. Dramix steel fiber reinforcement, 406560 VG, 40 pounds per cubic yard. Okay, going back and checking some of these inputs here. Some of these here, looks good. Click save. All right, loads, let's go in. So these loads, sometimes the program, when you switch between slab types, there can be a little bit of a, it goes back to some default settings occasionally. So I'm going to have to re-input this 18,000. No big deal. 42 inches by 12. See, that didn't change. 42 by 12 by 42. 6 by 6. Base plate. And then the load position, we're going to say it occurs not by the free edge, but by our primary joints and our slab center. So go down here. We leave that the same because we want to make sure the racks can occur right on there. We go back, check the wheel loads. The wheel loads reset. So we go back to 6,000, 36, 200 PSI. And we say that those can occur everywhere. So we got to make sure these are clicked properly. Go back. UDL did not change, so that did not get affected. All right. And there was no line load. I'm going to click save. And I'm going to calculate final result with my jointless slab. And we'll see how we go here. So with a 7-inch, 40 pounds per cubic yard jointless slab, all the same loads, we're at 82% utilized, which really means we could even look at going thinner if everyone was comfortable with it. But a lot of the times we don't want to go too extreme. So 82 inches or 82%, good value there, right? And again, as you notice, there are no saw cut results anymore. We've eliminated them. So the weakest part of our slab, we eliminated that with the jointless design because there are no saw cuts. That is the process in which you take a slab, you run it through, you get a design, you say, hey, I want to optimize it, cut down on the thickness using the yield line theory, right? That's what this tool is based on. We optimized the thickness down in the first case to 8 inches, saw cut with a little bit more steel fiber. And then we took that and were able to also present a jointless option to our customer as well. So we were able to provide 3 options, a 10-inch, an 8-inch, and a 7 at different fiber dosages, and the 7 being a fully jointless slab. It's a pretty awesome use of the tool. It's very much how we have always operated on our team. And now, once you're an advanced user, you have that functionality too. So now we're into the printing of the calcs portion. Pretty simple here. We just always want to make sure we're English US units. Because there's an English EN, and that'll be in metric. English US, English US, right? There's 3 different types of printouts you can do. Summary printout, extended printout, or a complete printout. The summary printout is a quick, and I say quick, but it's an 18-pager, right? But it's got everything you need. It just doesn't go into all the nitty-gritty about how we ran the calculation, how the tool is running the calculation. That's the summary. If I want the extended printout, print that. That one, if I can get to it behind this bar here. Hold, please. All right. There's the extended. It runs about 29 pages, right? The full calculation report runs 100 pages. So when I go in and print the full calculation report, I go from 20 and 30 pages to 100. It has everything in here, and it analyzes each and spits out all of the results involved with every single load case. Shows every bit of it, every bit of the information in here. You know, I just clicked to a random page. I got my allowable soil bearing capacity based on my 1-axle 2-wheel parallel to the secondary joint load case. Right? It goes through every single load case and produces all the output for that specific load case. And then you combine all that together, and that's why you end up with 100 pages. As opposed to your summary set is going to go through, give you all your basic information, slab thickness, joint spacing, dosage, which steel fiber, all that kind of stuff. Your applied material properties, so your load factors, all that information, all that good stuff's going to be in there. You can scroll down and look at your saw cut efficiencies. You can scroll down and look at your load applications. You can go in and see what forces were inputted, and then ultimately you're left with your results as far as your bending moments, your shears, that kind of thing. So the summary is great. The full calculation printout has everything and a lot more than the summary. And the extended is your middle ground. It goes into just a little bit more detail. So if we go back then to our slides briefly, we provided a saw cut solution, 10 inches, 19 pounds per cubic yard of fiber, 73% utilized. That sounds about right. We dropped 2 inches off. We're at 8 inches with 33 pounds per cubic yard of the same fiber. Got us to 95% utilized. That's the optimized design. Make no mistake in that case. 8 inches, 33 pounds per cubic yard is the right move. However, if jointless was on the table as we ran this option, and it drove interest from the owner, and it was worth presenting, 7 inches, 40 pounds per cubic yard, 66, but I think it was like 82. So that value, I didn't update that, or when I did my practice run, something went different, but 19 pounds per cubic yard, I got a few asterisks here. 19 pounds per cubic yard is the minimum dosage of Dramix 406560 for saw cut floors. 40 pounds per cubic yard is the minimum dosage of Dramix 406560 for jointless floors. And then the last one here is just the reduction in concrete, the reduction in inches off the slab. It's worth noting. For every 1 inch of concrete removed from your slab, you're going to realize roughly a 10 to 12% in your CO2 reduction. So you're talking about taking 2 and 3 inches off the slab. You're talking about 20 to 30% of a reduction in your CO2 as it relates to your slab. And for those that have owners that sustainability is a big driver in their design choices, this starts to be very powerful. We can calculate the CO2 savings, the actual numbers, not in this online tool yet, but if you give us a design that you've created and you're comparing it against a thicker section or rebar, thicker plus rebar, whatever, we can evaluate that and provide those sustainability calcs for you. And that's extra firepower for your discussions with your owner in these cases. So that was a lot. That was a lot of information. And I hope it was a good representation of how to use our tool, how you can expect to use the tool, what are some of the functionalities. Um, I think it's going to be great for our market. It's going to allow for you all to get a look behind the curtain and see what we've been doing when we've been trying to work with you all over however many years and run designs for you and all that kind of stuff. Now you get to kind of see how that works and the processes we go through and how we provide you the most optimized solution. Or in this case, we may present a few options, right? And show you could be light fiber, thicker concrete here, thinner concrete, a little bit heavier fiber here, get rid of joints, real complex kind of Cadillac premium jointless type of application as well. And provide those different options to your customers. And hopefully this is a really powerful tool in your all's tool belt as you guys are designing your industrial floors and your concrete flatwork anywhere. Remember, not necessarily limited to industrial floors, even though that's where we operate most of the time. There's certainly a case to be made that commercial and some light industrial, no problem at all on this. But if you have any questions as you're going through this, outside of the Q&A session we're going to do here in just a second, if you have any questions, need any support, we are here. Your local Bekaert rep is here. And we will make sure that we get any questions that you have answered. We can do follow-up meetings, all that kind of stuff. So with that, I'm going to kick off Q&A. But just want to say, thank you all for those that stuck around for this long. And I hope it was good information for you. I hope you think it's a powerful tool and hope to see you out there using it.
Awesome. Well, thank you so much, Hunter. That was great. And we do have some questions, so I will kick us off without further ado. Daria is asking, at what dimension would a free edge be a concern for rack loads?
So again, question is, at what dimension of free edge would be a concern? There's certainly a case to be made if your rack layout occurs at your free edge, and it should be evaluated, even if it's not a fully loaded rack. If it's close, if it's within 24 inches of your free edge, and we feel like that's, again, you as the EOR feel like it's enough that needs to be evaluated. The reason I didn't create it there is because I was basing it off of the fully loaded racks. They're not going to occur near the free edge. So therefore I know that it's not going to control. But again, that's a decision you as the EOR evaluate yourself and say, hey, if I got a pretty heavy rack that's going to be up against the free edge or 12 inches from the free edge, I maybe should consider it, then by all means, I would definitely include it. Some things that I do, kind of just typical practice, I usually hold like a fully loaded rack, let's say 30 inches off a free edge, just to see like where we're at and if it's going to cause a problem. And if I get a feeling that it's going to cause an issue, we need to drill down and make sure that we're not putting anything too close to the free edge and going to occur any kind of failure.
Awesome. And Hunter, it might be worth clarifying what a free edge is beyond just the perimeter of the building.
Yeah, so the free edge is any condition that the slab is acting essentially as a cantilever, right? So the slab is terminating, for lack of better words, and there's nothing that's going to transfer load beyond that edge, or, it's not a joint. I don't want to call it a joint necessarily, but beyond that edge, there's no transferring of the load into another adjacent panel. It's acting as a cantilever in that case. So that's what we mean by a free edge.
Right. So no turn down or grade beam at the perimeter.
Yeah.
Yeah. Okay. Awesome. Great. So next question, is the option to leave the slab unreinforced or reinforced with rebar only available in the tool?
So it's a good question, and it comes up a lot. And the tool, as I understand it today, is not going to be functional for that. And the basic reason for that is you can't run a yield line analysis on a rebar designed slab. If there's not fibers in there, you can't run the yield line analysis. And the tool is today, as we understand it, only based on running the yield line. I've been asked that same question by so many of you in my time at Bekaert, like, is there a box we can just check plain concrete? And there's not today. I don't want to say there will never be, but as of now, no.
Okay. Next question. The load to assign includes the load factor. Is there an option to develop a load combination based on the governing codes and standards?
Yeah, absolutely. So anytime you're dealing with something that you need to run through your load combinations, your building code load combinations, or anything like that, you have the ability to run those numbers and then input into the tool whatever that ultimate value is. And if you want to game it so that all you do is put in a load factor of 1, let's say, for instance, you run it through a load combination on paper and you get a value of 20 kips and it's all the way factored, from product load or whatever, live loads, whatever you're factoring, and then you drop that value that's been factored on paper into the tool, you can set the load factor to 1, and it's already because you entered the load factored as is. So you can set that value to 1, and now you're running the factored load, even though your load factor in the tool is set to 1.0. I hope that answered the question.
I think so. Yep, there's one other way to do it where you enter the service load and kind of an effective factor as well, right, Hunter?
Yeah, so you can enter in the service load and you factor it on paper, and you know that, let's say it's 20 kips is your factored load when you run it through all your load combinations. You enter in the service load in the tool, but instead of entering 1.2, let's say your effective load factor was like 1.4, let's say 1.45, 1.39, you can enter that in. So you're entering unfactored loads into the tool, and you're still just controlling that load factor to get where you want to go. So yeah, that's the other way to do it. Good point, Claire.
Perfect. Okay, great. Where I think you answered this at the end there, Hunter, where do we find detailed calculations for punching shear and slab bending moment capacity?
Yeah, so that's going to be in your calculation report. There's a section for moment capacities. There's a section for all your punching shear, and it's specific to, in the full calculation, it's specific to the individual load cases as well. So you'll be able to see the demand, say the demand punching shear from the rack load right out of saw cut, or for example, you'll be able to see that very specifically in your calculation reports. Yeah.
Perfect. All right. Beta is asked, I got failure in the soil unity check. So somebody's already using the software, which is great. Could you explain this type of failure of the soil check?
Yeah, so if you have a soil subgrade modulus that is not going to be able to sustain in combination with your concrete slab and your fibers, if the soil is not strong enough to support those loads, we have some other things we have to consider. We could go thicker with the slab. We could adjust the fiber dosages upwards, though that doesn't tend to help a whole lot. If your soil subgrade modulus is so low that, and at which you're talking, we have to just go to a different solution entirely, then we can go that's obviously a decision outside of Bekaert, but that could be the other solution, is that soil remediation, those types of things need to be considered. I've seen soil subgrade moduli as low as 25 PCI. So, but then it's a combination, right? The low subgrade modulus plus loads that then cause that soil beneath the slab to fail. You have to have both of those. If your loads are small enough, it could be okay. I hope that answers the question.
And I might just add to it, if you don't mind, Hunter.
Sure.
Since the soil check is a service level check, if you are, just based on that question that came up earlier, if you're entering your factored load with a 1.0 load factor and you have a soil failure, it may be worthwhile to enter the service level load, with the effective load factor of 1.5 or whatever it is, so that you get the soil check with the service level load, so that that's compatible.
Great.
All right. Probably our last question here. There are a couple of other questions, but we're just up against time. Do you have a document with typical fiber types and minimum fiber dosages, or different fibers and joint conditions?
So we certainly have some basic guidance that we can provide as far as it goes with minimum dosages and things like that. I made point to mention that we have our minimum for saw cut floors with that specific fiber, and then it's very possible that if you end up using a different fiber, then minimum dosage changes. So it's hard to give some hard and fast typical guidance there. But if you have a certain case that you want to look at that is outside of the 40, 65, 60 in a saw cut application, where we know that's a 19-pound minimum, we can definitely do that. There are guardrails inputted into the software that will not allow you to go below or exceed certain dosages. But if you have any specific concerns, my recommendation is just give us a shout, give one of us a shout, and we can do our best to point you in the right direction or consult you as best we can on that specific project. But good question. Yeah.
And maybe, Hunter, we have that that document that we've created in-house for some guidance on some of these. So maybe we can send that to the folks who've attended today so
Sure.
that they have that as well. All right, perfect. Well, we are at time. There's just one or two questions here remaining, but I think Hunter will just follow back up just so that we respect everybody's time here. We know you've been on the line for an hour and a half already. So Hunter, thank you so much for going through this with everyone. Folks who've joined us online, thank you so much for taking the time to talk with us today about this. We really appreciate you making the commitment to using this tool, and we look forward to working with you soon. Hunter, any final closing thoughts?
Nope. I appreciate you all and can't wait to work with you here in the future.
All right. Thanks, everyone. Have a great rest of your day.
Bye.